All right, so my name is Zach Magnone. I come from Tyco, and what I'm going to present to you on this morning is what I'm going to call a practical alternative method for designing and calibrating a virtual sprinkler spray in, say, a CFD package. So just a quick agenda. I'll give a little bit of background and introductory material, and then what I'm going to do is kind of give you a high-level overview of the methodology that we use to do this, and then go through some of the details by way of kind of a case study example. We actually use the method to design a residential sprinkler, and then we'll kind of close off the talk with summarize the results. So just to set the stage a little bit, I'd like to say, in this case, we're not necessarily interested in how the sprinkler spray is impacting the fire itself. What we're more interested in is how the sprinkler sprays are actually impacting the dynamic effects of the fire. And to kind of give you a little bit of an example, I threw up a quick sort of schematic of here you have a typical fire in a compartment. Let's say that fire has grown to the point where it's activated a single sprinkler in that compartment. Okay, and then there are sprinklers in adjacent areas. And we want to answer the question, let's say, for example, will these additional sprinklers activate? So we know that that's a pretty simple calculation to do if we know the local temperature and velocity information at those additional sprinklers, which is really what CFD is designed to do well. The sticking point here is when you go to specify the spray in this instance, there's a number of different characteristics that you need to account for. There's characteristics which relate to the spray geometry or how that water is distributed in space. We know that, for instance, the heat generated by a fire isn't distributed evenly within the space. So we know that the water, if we were looking at how we're going to cool off, say, the upper gas layer, needs to be distributed in a specific way. So that relates to the 3D spatial sort of distribution of water droplets. And the other ones are those characteristics which relate to the energy transfer properties of the spray. For instance, how they're cooling, things like droplet size and velocity, which relate to the evaporative cooling processes and things like that. So in order to put a sprinkler into a CFD model, like FDS, you need to determine these spray characteristics. So the direct approach, which I'll call it, which is really the most robust approach, is to go out and actually measure these characteristics directly. And you can do that using techniques like phase Doppler interferometry to measure droplet size and particle image velocimetry to measure velocity distributions and things like that. However, they require large quantities of data, and I think also at this point in time, a lot of these techniques are just reaching the level of maturity they need to be at to actually measure these in a robust enough way to do this. But this is really the most robust way to do this. You generate a spray based on measuring all these characteristics, and you can put those into a model, and then you validate that model using test data. Well, let's say you don't have any of that information, or the faculty or the ability to collect it. The approach I'm going to talk about today is a way of, for specific applications, going out and actually measuring the effects of the sprinkler on the environment, and then backing out of that some general spray characteristics you can use to actually specify your sprinkler spray in the model using, say, like I said, like some compartment test data. It's going to be not as generalized, but requires smaller quantities of data that you can collect using, I'd say, is more universally acceptable means. Okay? So the goal of the method here, or the goal is to design a virtual sprinkler spray based on a set of known performance criteria. We're going to call those target outputs, or you'll hear me refer to them later on as response variables. And the method we're going to use, we're actually going to borrow something from product development that has been used for years and years, which is using sort of statistical methods. There's this statistical multiple response optimization technique, which is just a fancy way of saying what we're going to do is actually develop and execute a set of very carefully designed simulations so we can collect data on the sprinkler effects in the CFD model for a wide range of input variable combinations. We're going to do that in a very specific way. And then we're going to use regression techniques to estimate the functional relationships between those inputs in the model and those target outputs you've gotten from some test data to create a system of just fitted y equals f of x equations. And then we're going to solve those simultaneously, essentially, to derive the inputs we'll need for the model, and in such, actually calibrate the spray for this particular application. Okay, so now, by way of an example, that was kind of the overview. The reason we actually did this, started this whole thing in the beginning, is we actually had, we were doing a research project, myself and my co-author, Rob Acosta from Arup. We're doing a research project. We're looking at fire-driven transport phenomena after a sprinkler is activated related to, let's say, the transport of toxic products of combustion from a fire. All right, and but we didn't have any of these direct measurements for the sprays that we were looking at. But what we did have data for were, say, floor distribution data and wall wetting data, which are actually measurements that are made when we develop these sprinklers in the real world. And we also had some tests we had run where we collected steady-state doorway temperature and velocity profiles with and without a fire with a sprinkler spray, similar to what you see up here in this is just sort of an FDS the domain, but you see it's just a compartment. There's a sprinkler in one end. There's a doorway here, and this is just a slice file showing temperature. In this case, and this will be important later, we had a warm, it was sort of a warm ambient conditions and a cool spray, so we got induced air currents without the presence of a fire, and that's the data we're actually going to use for this analysis. Let's see if we can, okay. So, in order to use this method, the first thing we need to do is select our response variables or our target outputs. And we want to do these in such a way that they are actually capturing those spatial effects I talked about before and the physics related to the cooling processes, okay? So there's a couple things that need to be to use this particular method. These response variables need to be continuously variable, easily measurable both in the real world and from, from your simulation data, and can be boiled down to a singular value. So spatial effects kind of need to be simplified, if you will. And I'll give you an example of that. So what we actually picked for our analysis here were these 5 response variables. You see the floor density and wall wetting height. We selected some target values there based on just averaging them from the data that was available, okay? And then for the ones, these are more the ones that relate to the, we'll call it the energy transfer processes of the spray, where the induced inflow and outflow velocities. See here you have this is a schematic of the compartment. You have a sprinkler here, the doorway here, and we actually measured the inflow and outflow velocities here that were induced. And what we did is above and below, say, the neutral plane in the doorway, and the established flow fields, we just averaged those down to get these. So these became our target outputs. These is essentially the design points that we're going to use to try to reproduce with our spray to through the process. So the next thing we need to do is then select our input variables. And these are basically the parameters in the model which are used to control the spray. So in FDS, these are the input parameters you're going to use to specify the different things like droplet size distribution, spray velocity, etc. So the first thing we want to do is identify the most critical ones, because you don't want to have, say if you have a set of 15 different parameters, it would be very difficult to do this because you'd have to run like hundreds of simulation runs to get your results. So 4 to 5 is good, and if you can boil it down to 4 or 5, then you have a reason why you're looking at tens of simulation runs, you can get your data and do your analysis. Once you've sort of picked your most critical inputs, then you're going to set some ranges for min and max values, and we're going to do this using engineering judgment. At the end of the day, what we want to do is end up with a sprinkler spray that when you look at the droplet size or the velocity and things like that, they are physically reasonable. And the way we can do that is going to either literature. For instance, for droplet size, we can look at Dave Shepard's dissertation that he did, where he measured spray characteristics for a wide range of different sprays. We look for one that's very similar to the type of sprinkler, for instance, we're looking at here. We can also use Hesketh's correlation, which is actually in the FDS user guide for actually selecting the median droplet diameter. And then from that, we can set a range of reasonable droplet diameters. The idea here is just to set some physically reasonable parameters that we can then use to set the bounds of our analysis later on. So we actually picked 5. 4 were directly from, we used in FDS, there's a, what I'll call the simple spray algorithm, which is you create sort of this, you have your droplet injection surface is just defined by a radius and a couple angles, which create a region where you're going to let the model inject droplets, or Lagrangian particles, essentially. So we have our droplet size, initial velocity, 2 angles, And then we actually threw water temp into this one because it was a variable that had a high degree of experimental uncertainty, and it's something you can do when you do an analysis like this. If you have a noise variable, we'll call it. Okay, so we selected these ranges. And the next thing is now we have our ranges, we're going to look at our experimental design. We're going to use sort of what we call a statistical design of experiments here. And without reading what it says up there, basically what we used in this analysis was a central composite design. And all that means is we're going to run simulations at both low and high combinations of our different inputs, okay, as well as some points in the middle so that we can test to see if there's not necessarily, this is what we're going to end up with is a regression equation at the end of the day. And that's either a linear, if you only run low and high, if you only have 2 points, you can only make a line, so you get a linear relationship. We know that the relationship, say, between droplet size and cooling probably isn't linear, so we use a higher order design. This will actually allow us to create a second order model that we can then use to test for curvature and create what they call a response surface, which would look like this for a two-factor experiment. So you end up, this essentially gives you your test matrix, and these are your simulation matrix. And you see all different combinations of our inputs, which are between those min and max values we selected previously. And in this case, we had 5, so we ended up with 32 individual simulation runs. So we execute those simulation runs, collect the data for all the responses, those 5 responses I showed you before. And then the next thing we're going to do, now we do our statistical analysis. So the first thing we do is we create that fitted function, which is just a regression analysis using the method of least squares. We'll create some y equals f of x equations. Here you see this is a second order, essentially least squares fit, where you have the y is your response variable, the x's are your inputs from the model, and the betas are your regression coefficients, okay? And the method we actually use is one that sort of was popularized by Derringer and such in the 80s, and it's essentially taking this equation, converting it to this desirability function where our target value for those responses that we picked earlier in the analysis becomes, we give that a desirability of 1. And then we know that our model isn't a perfect fit, for instance. So we set some min and max values of reasonable, like for instance, wall wetting height. We'll say it's okay, say if the target value is 1.8 meters. Well, we'll say plus or minus 10 centimeters is probably okay. And that could be based on experimental uncertainty, or that could be based on good engineering judgment. But we'll allow it to vary that much so that we can create this composite desirability down here. So you can see this is sort of a piecewise function where we see at our min value, we're at 0 desirability. We hit our target, we're at 1. And then if we go above our target, we get back down to 0. And we can take all these for each one of our response variables, create this composite desirability using the geometric mean. And that gives us a single function that we can maximize for this delta. And from there, we can actually extract the optimum set of inputs for our model that will essentially create our virtual spray. So this is sort of the overview of the method. There's a lot of math and equations here. You don't necessarily have to read them. This is in the paper. And also this paper by Derringer and such is very good when you're doing this type of an optimization technique. This is all done using a computer, basically. Makes it very simple. All right. So, going through this process, it actually spits out the, optimum parameters for our sprinkler design that should, in theory, meet our target outputs that we selected originally. So here's for our residential sprinkler, we ended up, say, with a droplet size of 870. This should be microns. It got rid of my mu for some reason. I don't know why, but. So this is our ultimate sprinkler design. These were the targets that were used to generate it. Now our model isn't a perfect fit. So we see this is the prediction, which is based on these parameters and what they should be based on the actual fitted model or those fitted equations I showed you. And what we do now is we take these, whoops, what did I do? There we go. Stick these, apparently 4 years of engineering school. And anyway, so we stick these into our FDS simulation, and then we do a validation, and actually what it spit out were these values here. So you can see how closely, using this method, we're able to reproduce the floor density, the wall wetting height, within, let's say, 3 centimeters, okay? The inflow and outflow velocities, which essentially allow us to stretch these profiles to fit this data here. These are the spatial distributions or spatial profiles of temperature and velocity in the doorway. And finally, the outflow temperature. So basically, with 32 simulations, about 2 weeks worth of work, we're able to calibrate this, design and calibrate this spray for this specific example where we're interested in just these gas phase effects. So for a little bit of further validation, this is going back to that study I was telling you about before. We were interested in toxic products transport. We actually did a little experimental study. We had a compartment, a very similar compartment. We just attached a corridor to it, and we actually measured temperature, velocity, and actually CO concentration. We seeded CO using, this is all done steady state. We actually seeded CO into the fire plume, so it wasn't necessarily the fire creating the CO. It was just a species we could track. All right, and we stuck the sprinkler in, and what we find now with this calibrated spray is we're getting very reasonable reductions, say, in the change in temperature is very close to the right, it's right delta T, even though some of our, say, boundary conditions for our simulations weren't perfect because of the complexity of the experiments. We still see the right change in temperature, the right trends in the change in velocities, for instance, and the right trends in, say, the change in the species that we're measuring in the flow. So, you know, there isn't necessarily a rigorous uncertainty analysis that was done here, and I know that. But just to show you an example, now we've gone through this process. In 2 weeks' time, we were able to actually create the sprinkler and had something we can use for the analysis. So, just to summarize, you know, we know the spray algorithms and CFD programs rely on a large number of input parameters that you have to go out and measure using these complicated techniques. And there isn't a lot of published data out there that you can use, but there isn't some that you can use to kind of guide this type of analysis, where instead, if you have access to some performance data, you can go and actually set up this carefully designed set of simulations and extract those optimum parameters using this optimization technique. And the impact of that for us was it's a predictable time frame for the analysis. It only took us 2 weeks, and we knew if we were rigorous about how we did this, it's not like the guess and check that I use all the time, and you never know how long it's going to take, or doing something like a Monte Carlo simulation, or using a genetic algorithm to do the same type of thing, which can require hundreds or thousands of experimental runs. We did it in 32 here. We got a very reasonable result, and we leveraged, for most of that work, inexpensive computational time versus lab time. So just to, I'd like to acknowledge my co-author, Rob Acosta, who was very instrumental in a lot of the work that we did here, as well as the additional support I got from Professor Nick Dempsey at WPI and Tricia Boyer. So, thank you.
Thanks. Do we have any questions? Randy.
Very interesting talk. The floor density looked completely off to me. And you sort
I knew
of
I was going to get a question about that. Let me go back to that slide, actually. So it looks completely off. It's not that. The issue here is there's no scales on these graphs. But we know that we're actually creating a very idealized, you know, there's a big simplification here in the density. Like I said, I'm not worried about where I'm putting water on the surfaces, but I'm getting the right proportion of water, in space for the most part, between the floor and the walls. So some of the things that throw this off too is you have like frame.
There's some moments of the distribution that you're matching, I guess, is probably the best thing you can say about that.
This is a simplification. For gas phase stuff, I'd say this is okay. For if you were worried about like wetting surfaces or complex geometries, it probably wouldn't work so well. So.
That leads into my question, and that is, you know, in this case, how good is the assumption that the spray is actually symmetric? Is the sprinkler a conventional design, or is there something about the strike plate? I know the frame arms are going to throw things off a little bit, but it looks like it's more than just the frame arms that are having an effect here.
Yeah, well, in the real world, you do have some high spots because of this here you have frame arm interactions, for instance, and you also have you know, the influence of slots and tines plus some shadowing from the frame arm. So that's something that you could account for. In this case, we were just looking at having a spray that would give us the right sort of gas phase type of cooling and impact. There's nothing saying that you could use, for instance, a table and create some simple regions and use the same type of analysis to get a little bit more complex spray.
Yeah, there's going to be more variables you have to play with.
Yeah.
Okay, thanks.
Any other questions?
Jim's got a question in the back.
You know, predicting the results without the spray and then with the spray to show the difference, I think that would be an interesting comparison. You know, to show how much is the spray actually affecting the temperature distribution in your case.
Yes, so in this particular case, we used data that was collected without a fire. So it was a warm ambient condition, a cool spray induced. So that we were interested in this case, we're trying to collect distribution data at the same time as sort of our temperatures and velocities. So we were worried about if you had the fire, that could cause some evaporation and things. But in this case, we actually we stuck this spray now into this scenario where we had a with and without a fire, with and without a spray. And you can see there's experimental data are the points here, and then the lines represent the model data. So what would be good to do, and I agree, would be to do more of a rigorous sort of uncertainty analysis associated with this result. But in general, it's doing a fairly good job. I don't know if you answer your question. Mm-hmm.
Is there any like a practical table for day-to-day engineer working with this thing? Or obviously we know it's a difference if you deal with a residential sprinkler or we deal with a warehouse. It's totally different animals, but I'm not so sure how the FDS deal with it. I'm sure it's flexible to input some custom data there, but for day-to-day practitioner engineer, this is like a high-end kind of research, but is there any like a one-page table which would relate what we have to actually plug into FDS in relation, okay, for the K factor 5.6, 4.9, residential 11.2 for storage, or if you're moving up to SFR, or based on the design pressure, something, because when I read this, I got so excited, I see this thing, and it says practical method for designing, you know, but for day-to-day engineer, it's great. That's a research. So what is it for which we could use? So let's say we do the alternate solutions for the building or for the warehouse solutions, and we'd like to use FDS.
I think what you're describing is the nature of the problem, which I've heard a lot, which is that, you know, there's really no reference material you can go to for a particular manufacturer's nozzle or whatever to go get these parameters. Most manufacturers don't want to publish them. Working for a manufacturer, we have a lot of proprietary products. They won't let me publish them.
Okay, how about if I spec? How about if I spec 5,000 of your ESFR heads on alternate solutions somewhere? I'm sure I would be able to get the data, because some manufacturers, they give it away. Like it's been always a struggle. Like 10 years ago, a response time index was the big magic. To get a response time index directly from the manufacturer was like a pulling of weeds. Mm-hmm. Right? So now they kind of publish it, even detection manufacturers somehow. I was able to obtain it for different detectors. But with Sprinkler Award, like, how can we actually translate this thing into day-to-day life using FDS when we work in this?
The nature here, I just wanted to present kind of an alternative to going out and measuring all these things directly, which we can do. When we do that, we're in the process. One of the things, the next phase of this is actually to take these sprinklers, measure all these parameters, and compare them to what we got using this method. That kind of would close the, sort of close off the analysis in a nice way. But here is just a way of...
Let me rephrase the question.
Right.
So this data is proprietary, but is it available? Like, has it been done, or is it still in a research stage?
The data that is presented here? Like for this sprinkler, or?
No, let's say, Tyco has a
Oh,
line
okay.
of
So the performance data that we use.
performance data. Like
Yeah. So the data we used here, actually, this doorway flow data here, we actually did that. That was done as a student project. That report for a number of different sprinklers in a number of different fire scenarios is available publicly from WPI. So it was done as a student MQP, and all the data on this doorway flow data with and without sprinkler sprays, with and without fires, are actually available. So rather than publishing the actual spray characteristics that we measured for this particular spray, we published some data related to the performance. So,
All right, thank you,
I don't know if that
Zachary.
answers your question, but thanks.
Thank you, Zach.